Just a general question.
It said like part of it was in gas form and part of it was in aqueous form. So it had 1 molars and it had pressure in ATMs also in the same one. They wanted you to find the Q.
Okay, we could do an example of something like that.
Number 37, part B goes from Ag solid, single mark, Ag plus, 0.34. The bridge, Cl minus, 0.098 M, and then chlorine gas, 0.55 ATM.
All right.
And then the metal on the chlorine gas side is platinum.
But do they give the, what was the Ag plus concentration?
0.34 M.
And did they give a chloride concentration?
Chloride, 0.098 M.
All right, so we just write our standard cell, anode to cathode. It just goes alphabetical. And then oxidation and reduction. Oxidation always occurs at the anode because we've got to generate the electrons here. And so silver is not the greatest reducing agent. You know, oxidation occurs for the reducing agent. So we oxidize silver to silver ion. So we need a powerful oxidizer to do that. Chlorine is chlorine gas.
Is it powerful oxidizer?
2 units.
Oh yeah, 2 electrons.
I'm sorry? 37B.
37. We could do this cell diagram for this one. You know, silver solid goes to silver ion. Since this isn't under standard conditions, if it's not under standard conditions, we should write the concentrations in here because it's going to impact. And then the salt bridge. And over here we're going to have chlorine, gas, 0.5 ATM. And then chloride is AQ, so...
They use a comma on that one because of the platinum wire.
They use a comma there because of the platinum?
Yeah. It's the same thing.
Alright. Usually commas when we have the same state. That's alright. This is chlorine gas goes to chloride, and then we'll have platinum. This is the electrode. The chloride, we need the concentration there. It's not under standard conditions. The concentration for the chloride is 0.098 molar. So this is an example of a non-standard condition. So what are they asking for, the voltage?
Yes.
So if we put a voltmeter here, how many volts are we going to register?
They use nerds.
Yeah, so we're going to use the nerds too. E of the cell is equal to E0 of the cell minus 0.0592 volts over Z or N. Z log base 10 of Q. So the first thing is we need to figure out what the E naught of the cell is, under standard conditions. Okay, but E naught of the cell is, we just add up the anode potential.
Going together is the 0.558. Oh, sorry.
Well,
I was getting ahead.
is E naught of the cell pretty easy?
Yeah, they give those in the appendix B.
Yeah. All right, what is it?
I have it at 0.558 volts.
So we just plug that in there. Z, what's Z for this? For Z, we have to add up the 2 equations to get the net reaction. To add up the 2 equations, we need to multiply the first one by 2. And so the net equation is going to be 2 silver solid. Because the number of electrons produced have to equal the number of electrons consumed. plus chlorine. Yeah, so Z equals 2. 2 moles of electrons transferred in a balanced redox reaction. And then we need Q. Q is the activity of the products over the activity of reactants. So the products we have, the activity is silver ion squared. This is QEQ. Activity of the chloride squared. Divided by the activity of silver, solid. Silver solid is
It's
1. So this goes 1. Well, way back when, I forgot which chapter. Activity of the concentration.
Chapter 15.
Chapter 15. Silver ion squared. Chloride ion squared divided by the partial pressure of chlorine gas. So we have both concentrations and pressures in the equation, so we just plug it in. Concentrations are going to be molar, pressures are going to be ATM or bar. It depends on what the chart is. If appendix D is in bar, then we should use bar. If appendix D is in ATM, we should use ATM. Both charts are very common.
So I guess how does that turn out to be volts?
How does that turn out to be?
Yeah, the 0.092 volts. I see it now. I was trying to get molar times 4 divided by ATM to get a volt.
Well, the units are actually in here because there's in this 0.0592 volts, there's a mole term here, which they didn't show because that's RT. What was it again? It was RT. Was it? Anyway, it's RT ln Q. Is that it?
It's they start out as negative ZFE plus RT on Q.
No. And so it's RT over F. There's a mole term that's not canceled out. Or is it? Maybe it is canceled out. But R is joules per mole Kelvin. T is going to be in Kelvin, so the Kelvins cancel out. Faraday will be in coulombs per moles electron. I guess the moles cancel out. Huh?
Yeah.
So Z, I guess we'll just say joules per mole. Then because a volt over a coulomb equals a joule. Because a joule is equal to a coulomb times a volt, right? I think. No, that's wrong. Is that right? Or wrong?
Yes, I remember.
Volts is joules, yeah.
All right. So we just plug in all the numbers and then calculate. Okay, other questions?
Oh yeah, for number 18 on the practice exam.
Number 18 on the practice exam.
You expect us to find a free variable for something.
Uh-huh.
On your cell diagram, if it changes state, then you add a bar.
Yeah. This should be a bar
Okay.
right here. When it changes state, it should be a bar, but in that particular problem, they put a comma. Yeah. If it's in the same state, like tin 2, tin 4, you put a comma.
You want us to put the molarity in the atmosphere?
If it's non-standard, you usually put the molarity in the atmosphere. Usually, you don't always have to. The situation is when you have a cell like this, the molarity in the atmospheres is always changing, and so if you put it, you're just taking a snapshot. At this time, this is what's happening. You know, a reaction, I might say, you know, you start off under standard conditions, and after 50% reaction, what is the voltage? You know? After 50% react, well, under standard conditions, everything is, you know, initially everything is, yeah, 1 across the board, and so after 50% reaction, the reactant's gone down, you know, 0.5, depending on what the limiting reagent is. Products have gone up 0.5. Yeah.
It's way on the top.
Oh, the top one? Which exam was it?
Chapter 20 exam. Now, it was like fall 2013.
19B20 or 19?
Um,
I think it's
20.
all 13.
Pull that down, Kelly.
I know, I'm about to pull that down.
Oh, here, I'll get it.
Oh no, I'm a rocket.
Here.
Yeah.
All right.
Thank you, Kelly.
All right, not this one then. This one here. Number 18.
18.
They can't be this one either. Is it?
Come on, let me just go on there.
Is it? Wait. Is it chapter? It's this
Chapter
one.
20. Yes.
I think you're on chapter 19.
Yeah.
On the top.
On the top. This one?
Wait, okay.
That's
No,
the name
just
for it.
go on there.
I think you might be in the wrong post.
Oh, did James? Did you post the 20? Yeah. All right, that's fine. Thank you.
Okay, wait.
All right, here. I need to refresh it. Can I refresh it, Kelly?
Yeah, there you go. Yeah, there you go. That one, number 18, yeah.
All right. Yeah. Was this which?
Question 18.
All right. For question 18, for the reaction CH4 plus 2 O2s yields
Wait, how come just do number 18?
Which one? are you
because
talking about?
that's a typo. I made a mistake.
Number 18 and number 19.
All right, let's take a look at this. So this is a redox reaction. Any redox reaction we can use to generate electricity. Let's see, it's methane plus O2 yields CO2 plus water. Delta G naught is minus 18. What is N? What is E naught of the cell? And so what is N? N is the number of electrons transferred in the balanced chemical reaction.
Oh, I thought it was like the moles of gas or something.
Well, yeah, sorry. You know what? Just Z. What is Z? That's what I should say. You know, I get into the habit of writing N because used it for many years, and then one year it's changed to Z. Well, it's moles, and N just represents moles, you know, of anything. Usually, it doesn't have to be gas. It's moles. And so, what is Z? The easiest way to determine Z is just use oxidation states. The easiest one to use is carbon, because carbon is only one species here, carbon's one species here. If carbon made multiple species like CO2, CO, C, you know, then it's a hassle. But we want one atom that changes. So, you know, here's our oxidizer, here's our reducer, or we could use O2. But it's easier to use C because there's only one atom. The O2 is going to give us the same thing. And so did somebody calculate Z? All right, so what's the oxidation state of carbon and methane? Now, somebody was asking me, how do you do oxidation states? Who was that? Davin? All right, let me just go through how to do oxidation states.
Sometimes it's -4, sometimes it's +4. I don't know the answer.
Basically, there's like 5 rules you follow. 1, no, elements in their elemental form, 0. 2, in compounds, hydrogen gets +1. Yeah. But, you know, there's a whole bunch of rules, but hydrogen usually goes first, and then the group 1 are +1 in compounds, and then you go on. There's other rules. Like when I was learning oxidation states, I learned this one: the most electronegative element gets its standard charge, then assign everything else. But you know, sometimes, especially when you go into organic chemistry, you don't want the average oxidation state of all the carbon atoms in a molecule. You want to know what the individual oxidation states are for each atom. That way you can look at the reactivity of different parts of the molecule. And so this is what I showed. I mean, this is what I show my Chem 1A. So in Chem 1B, I didn't want to spend that much time on it. But you draw out the molecule like this. An oxidation state. What is the basic assumption for oxidation states? You know, the main premise of oxidation states is that we assume equal distribution. No. Oxidation, there are 2 extremes in bonding. What are the 2 extremes in bonding? We can have a covalent bond, or we can have a ionic bond. Most bonds lie between the 2 extremes. So this is what I mean by knowing the whole range of the forest. You know, you know the range. The limit is 100% ionic bond. The other limit is 100% covalent bond. Everything else has to fall between those 2 extremes. And so we don't want to figure out where the gray area is. We're just going to assume it's going to be 100% ionic, or we're going to assume it's going to be 100% covalent, and then look at the electron distribution. This is why we never compare oxidation states with formal charges, because formal charges look at it from the totally opposite extreme. The oxidation states are very useful, even though we're making everything extreme, because it's kind of a level playing field. Although it's not going to be totally accurate, because you know the accurate picture is you don't have a full -2 charge on the oxygen. You can see that, you know, in the Spartan lab. Normally what I make people do is I make people calculate the oxidation states by hand and then compare those with electrostatic charge to see what the difference in the oxidation states they calculated by hand versus the actual charge, or more accurate value of the actual charge on the molecule to see. You know, it's not 100% ionic, it's not 100% covalent, it's somewhere between, like 50% covalent, 60% ionic, or some other combination. You know, that's important for a reactivity. But anyway, we assume it's 100% ionic. 100% ionic means that the more electronegative element takes all the electron. And so it's called winner takes all. So which one's more electronegative, carbon or hydrogen?
Carbon.
Carbon. But you learned that carbon and hydrogen essentially have close to the same electronegativity, 2.5 for carbon, 2.1 for hydrogen, which means this is nonpolar. This is classified as nonpolar covalent bond. This is much closer to being 100% covalent than it is to 100% ionic. But what we're trying to do is we're trying to understand the properties of this by making a fair comparison with other molecules. And so we're going to say winner takes all, which means carbon has just taken all the electrons, so carbon ends up with a total number of how many electrons?
8 electrons.
8. How many is carbon supposed to have?
4.
4, so it has 4 extra electrons. Each extra electron is a negative charge. And so that means carbon ends up with a -4 oxidation state. Each hydrogen lost 1, it's supposed to have 1. All the oxidation states must sum up to the net charge of the species. How about CO2?
Question.
Thank you. Thank you.
Well, in this case, who's the winner? Oxygen. So oxygen takes all, and that means that carbon is not -4, +4. It's lost 4, so it's +4. In order to go from -4 to +4, how many negative charges did we just lose? Not 4,
Hey.
Wow.
-8. We have to do -8 electrons out the carbon. This is why I say methane. Methane is electron rich. Methane is a good fuel, a good reducer. And so, yeah, we lose 8 electrons and going from CO2. You see that? Where did those 8 electrons go? Oxygen. Oxygen. And so altogether we have a total of how many oxygens?
2.
2 times 2, which gives us 4 oxygen atoms. Altogether we have 4 oxygen atoms gaining 8 electrons. So that means each oxygen atom must have taken 2 electrons. Each oxygen atom takes 2 electrons. There's 4 of them. That gives us a total of 8 electrons. And so what that does is it converts this. What's the oxidation state of O2?
0.
0. And the oxidation state of oxygen and CO2? -2. The oxidation state of oxygen and water? -2. Both of these are -2, so we go from 0 to -2. That's a total of 4 oxygens. 2 of them end up in CO2, 2 of them end up in water. And that's where. So we could have assigned it based on the O2, but that's a bit of more headache because there's multiple atoms and then we have to divide it. Whereas carbon is just a single atom. Right? But
Wait,
both
what
of
do
them
you
give
mean?
us the exact same answer. The number of electrons transferred was 8 from methane to oxygen. Kelly, did you have a question?
Yes, yes. What do you mean that carbon is the single atom?
Well,
I see it.
no, okay. Actually, you know, it doesn't really matter what we do. Oxidation state is always for a single atom. It's the charge on a single atom. And so over here, we see that carbon went from, for oxidation states, we usually use Roman numeral. So carbon went from, actually, how do you do a negative? Just do it like this. CH4, carbon went from -4 to +4 here. But oxygen, we have 1, 2, 3, 4 oxygens. Each oxygen is a 0. I have to say this because some people think that the oxidation state of oxygen is, you add these up, you know, whatever that is. And so some people will say the oxidation state of oxygen and CO2 is -4. -4 is not called the oxidation state. You know what -4 is called? -4 is called the net negative charge. You know? The oxidation state of oxygen and CO2 is not -4, it's -2. This is a very common error in Chem 4 and Chem 1A. Less so in Chem 1B. And the same thing, this is easy because they're single. So, you know, because of the multiples here, it's a bit more of a pain. So each of these is a -2. And then we have 2 oxygens from the water. Each of those is a -2. And so each oxygen went to -2. So this one gained 2 electrons, this one gained 2 electrons, this one gained 2 electrons, and this one gained 2 electrons for a total of 8 electrons. Whereas that carbon alone lost 8 electrons. Okay. So this is why immediately I saw it's going to be easier just to do it off carbon. Are you not going to have half? You're going to have half reactions. We could break this up into half reactions too. If you want to break this up into half reactions, then this is what we.
That would be even easier.
It's just takes a little bit more time, you know, than just looking at the oxidation states, but maybe there's less error. How do you break this up into half reactions? Well, CH4 goes to CO2, and the other half reaction is O2 goes to H2O. And then we balance it. The carbons are balanced, so that's okay. And then what do we balance next? Yeah, we balance the oxygens, right? And so plus 2 waters. And then we balance the hydrogens. 4 plus 4 is 8 hydrogens, 0. And then we balance the charge. How do we balance the charge? Plus 8 electrons. And so the balanced half reaction is here. Let's write it in the light up here. It's CH4 plus 2H2O yields CO2 plus 8H plus 8 electrons. Then we go over here for the O2, and we balance this one. And so we have 2 oxygens, we'll need 2 waters. Then we have 4 hydrogens, we'll need plus 4H plus, right? And then we'll need 4 electrons here.
Wouldn't that be 12 electrons?
Wait a minute. I want to talk about it. The answer is no, it would not be 12 electrons. Why? Because you have to look, electrons produced must equal electrons consumed.
Okay.
We produce 8 electrons, we consume 4 electrons, so we need to double this. So we produce 8 electrons, we consume
Oh,
8 electrons.
now it all clicks.
Now it clicks?
It clicks. The first method you do is kind of confusing, but this
Well,
one clicks.
there's multiple methods, as for any, you know, like in math or whatever else, and multiple methods you could use to solve problems. So the more methods that you expose yourself to, you know, the better. And the more methods that you expose yourself to is just versus doing it all one way. You know, if you do the oxidation, you should get comfortable doing oxidation states, you know, either way. You know, you can follow the rules in chapter 5 back in Chem 1A, or you can do it this way, you know. Sometimes it's a trade-off. Sometimes I'll just use the rules in chapter 5. Was it chapter 5? No, chapter 3.
Wow.
What was it, chapter 3? The rules for the oxidation states?
There's a printout.
There's a printout?
Yeah, we got a printout.
You got a printout?
Go with her.
Yeah, it was from first class is a printout of the oxidation rules.
That's not even. Use the printout, that's fine. There's a set of rules in chapter 3. It is chapter 3. I don't remember. You can use the set of, sometimes that's way quicker. Way quicker just to use the set of rules and just get the average oxidation state. That's quicker. You know, but there's some strange stuff, you know. Like magnetite. You know the formula for magnetite? What's the formula for magnetite? This is the problem I love to assign in Chem 1A. Name that. Well, no, unfortunately it's not iron 3 oxide. Okay, we know oxide. Oxide's -2. So this is an alternate way we could do it. You just do oxides -3. We have 3 irons. The 3 irons have to add up to a net charge of, this is -8, so it has to add up to a net charge of +8. And so each one must be +8/3. +8/3. +8/3. So what is it? What's the Roman numeral for
2.6.
2? Roman numeral 2.6.
6, 7. Yeah, whatever.
Is that it? Or maybe we just do it like this. Roman numeral 8 divided by Roman numeral 3. That works. Roman numeral 8/3. Well, the problem with the oxidation states like this is the average oxidation state. We don't want the average oxidation. We want the individual oxidation states on each atom. And so we lose information. Whenever we average it, we lose information. Sometimes we try to retain that information by coming up either with a standard deviation or a 95% confidence limit because we don't know how much to trust that average. Whenever you're given an average, how many experimental data points did they use to come up with that average? You know, and what was the spread? You know, what was the smallest of the values they averaged? What was the largest of the values they averaged? You know, and so if you're given the average bond length, tell me what the spread in bond lengths. If you're given the average bond length for an carbon-oxygen bond is this, well, you know, how big of a spread do you expect? What's the smallest carbon-oxygen bond length? What's the biggest carbon-oxygen bond length? And what's the distribution of the carbon-oxygen bond lengths? You're missing information, you know? And so this is why for averages, we're missing information when we average things sometimes. And sometimes, you know, we gain insight. As averages are very useful anyway. But let's continue on because I don't want to do too much of this the oxidation states. Although,
the ultimate goal is to find delta G.
huh?
The ultimate goal is to find delta G.
Right. And so once we do that, we're almost there. Because what else do we have to do?
Oh, well, since you created the formula for the CH4 plus H2O plus, where that goes to CO2, you need to find the voltage on that.
Yeah.
The E naught.
Okay, so we figured out Z, right?
Yeah, we have Z.
We have Z, this is 8.
Yeah.
Now E naught of the cell. E naught of the cell is equal to minus Z F E naught. Oops, no, that's not. Delta G naught of the cell, sorry. Delta G naught of the cell is equal to minus Z F E naught of the cell. Therefore, E naught of the cell is equal to delta G naught over ZF with a negative sign around. And so we just do this. A negative times a negative 818. 1,000 joules divided by Z, which is 8, divided by F, which is 96,485 coulombs per mole. And so the moles will cancel out. This gives us joules per coulomb, which gives us volts. So this is going to be how many volts? You just calculate.
Oh, I thought we used data from the appendix.
That's chapter 19, so I try to make your life a little bit easier just by giving you a delta G naught.
Okay.
Although you should know, of course, you should know how to do it. If I did this under non-standard conditions, we could be more involved. All right, what was the other question? Was there another question?
Number 19.
All right, which is 18, number 2.
Yeah.
This is Appendix D data, I think.
I thought we don't use appendix D. And
Oh, you're right. You know what? You aren't going to have Appendix D. Now I remember this test. A lot of people left this problem blank. A lot of people left this problem blank and came up to me and asked me, you know, what is, I need the delta G's of formation, or I need delta H, or I need delta S. You know, I need those numbers. And I said, sorry. I don't have those numbers for you. You know all I give them? Yeah. I just gave them the reduction potentials. But they couldn't make the connection between reduction potentials and delta G. And so they were unable to solve it. It was like about 5 students were unable to solve it. But this we can calculate E of the cell for it quite easily. E naught, because this is standard conditions, E naught of the cell is equal to E naught of Well, you know, the anode. The anode is where oxidation occurs. So we're going from silver to silver ions plus the cathode. The cathode is going to be where reduction occurs. This is iron 3 to iron 2. So we produce electrons here at the anode, or the, you know, we call this the oxidation potential. You know, so there's three ways we say that. This is E naught silver to silver ion couple. This is E naught of the anode, or this is the oxidation potential for this reaction. And the same thing over here. This is the cathode potential, or the iron 3, iron 2 couple, or this is the reduction potential. Oh, Kelly, you'll be my personal assistant. Just need a cup of coffee. But anyway, so we look at the chart here for this. Iron 3 to iron 2. Do we see iron 3 to iron 2?
Yeah, it's
I don't see it here.
no, that chart. I have it here. It's on page 872.
Oh, here it is. So here's iron 3 to iron 2. Iron 3 to iron 2 has a reduction potential of 0.771 volts. Yeah, silver's right above it. So, write this. This is going to go, so 0.771 volts, and then silver is right above it. Silver is but you know, it's silver to silver ion. So silver to silver ion is going backwards, so we have to change the sign to 0.800 negative. And so this is not going to be spontaneous, because this is going to be a negative 0.029? 29 volts. All right, that's E naught of the cell, but the question is not asking for E naught of the cell. The question is asking for delta G naught.
And then we use the equation that's next to 2.
Right, and so the equation is delta G naught is equal to minus NF E naught. And so, oh, Z, minus ZF E naught. And so what is Z for this reaction? Did I erase it?
It should have been.
Well, you could just see it. How many electrons are consumed by iron 3? 1. How many electrons are produced by silver?
1.
1. So Z is
1.
1. It's balanced. So, and then just plug it in. Watch out for units. What are the units going to be for this? Joules, right? Joules. Okay, what else?
I think that's it.
That's it?
Anyone else have any more questions about the practice exam?
Spend all day on it.
When did you, James, when did you post that?
Because I didn't see it yesterday.
Hey!
Oh, you did? What time did you look? I looked at it.
Wait, he posted on Sunday, I guess. When it left me up.
You know, going through the practice exam like this is, I don't like to do, but I'll do it if somebody asks me. I don't like to do it because you should treat it like a real test, you know. But it's all right. If you have other questions, I'll just answer it. But, you know, I used to post the key to those, but people just end up studying that. That's it. Then I have to, if they do that, then I have to change the exam significantly.
Oh,
Make sure no questions match, you know, in format or. But I don't want to do that, you know. But I will do it.
No.
If people insist on having the key to the practice exam, then I'm definitely going to make the real test
It's in the
totally different. Not to be mean or spiteful, but
maybe we would have taken you up in the beginning.
Professor,
uh-huh.
could you just put like the solution, like just the value?
I don't want to put the value there because you got to, if you don't have confidence in your answer, then you got to gain confidence. And the way to gain confidence is to go back through the book and make sure you understand, I'm solving this correctly. And therefore, because the reason I want you to do that is, that I'm sure I'm solving this correctly. And let's say, well, actually, the reason I'm doing that is because, everybody makes mistakes, and you want to catch those, be able to catch as much of those mistakes as possible. And so, for example, in the solutions guide, there's mistakes in the solutions guide, which I didn't point out. I just want to see who catches them, who doesn't catch them, although I should point it out because people who don't catch them will have the wrong sense. And so it would be nice to, if you're not feeling so sure about a particular answer, to go back and review that topic more, so that by the time you've reviewed it, then you can be sure, I'm sure I'm doing this problem right, and the other thing is just to go back and double check. But having said that, I know that a lot of people, time is always a constraint. So if you're unsure about a problem, then just ask me in class about that specific problem. But I don't want to post the answers, I don't want to post the answers. I'll tell you, I got in the same thing. When I was a student, I was always able to ask somebody, what's the answer to this? Am I doing it right? And then when you get to a certain level, like upper division, then there are no answers. You have to come up with some other kind of argument why you're right. You're not right because you got the same answer as the answer key. You're right because you did this. That was the same kind of thing I was looking for in the formal report. I was trying to get people to shift from this mentality. Okay, these are the equations. A lot of people, they just focused on the percent yield and where they lost, or where they gained, or contamination, or that. But that wasn't the argument that I was looking for. The argument that I was looking for was that I got this because I did these steps. And clearly, looking at this, there's some logic as to why you expect to have this product and why you expect the purity to be high. Even though was there an answer in the back of the book? This is it. No, you have to come up with these kind of arguments, and that's what you're going to have to do a lot of if you continue in science. Because people are going to challenge. Science is self-policing, so people are going to challenge you not because they're mean or they're trying to get at you. It's just because that's how science works. You got to be hypercritical of everything that comes across you. And so immediately when you turn this in, a paper like this, people are going to ask, well, I don't understand why you're getting this. Why should I believe you that this synthesis works? This kind of thing. And so you make arguments about why somebody should believe you. It's just like the titration. And I'll tell you, the formal report and the titration, about 10% of the people will just give me the volume at the equivalence point. They got this volume and then spend all their time talking about, something else. But, they don't tell me how they got that volume or why I should believe that's the correct volume. Why I should believe that they analyzed the curves properly. Do you see? And so you have to make a convincing argument for that. Well, that goes for this practice test. If you have a question about, you don't feel certain about this particular problem, I'll post the answer if you want the answer.
No,
But,
not doing that.
Well, that's what I advise, but you're still learning, so it's okay. When you get to a certain point, nobody's going to help you.
with the answer. You have to come up with the answer yourself, and you have to argue that answer in front of a bunch of hypercritical people, that are going to challenge. This is what the oral examinations are about when you go. Actually, as an undergrad, did I tell you about my oral? I had one oral examination at UCLA when I was getting my bachelor's there. Did I tell you about that?
No.
Okay, during the oral examinations aren't common, unless when you go into grad school, then of course they're common. But I had an oral examination. I was in front of 5 people, and then they just, they want to grill you about certain things. So they asked me, it's a very simple question. It should have been a very simple question for a chem major. What are the chemical properties of phosphate? What are the chemical properties of phosphate? And so then I'm thinking back. Okay, precipitation, neutralization, effervescence, decomposition, combination, single replacement. Thinking back through all these things, and I couldn't come up with it. I mean, I'm the only person standing there, dead silence. These guys are waiting for an answer, just going through in my mind, and it was just these random, things. It wasn't any kind of, if somebody asks you a simple problem, because when I was thinking, there are thousands and thousands of different reaction types, how can I possibly? So I just said, phosphates, used as a precipitating agent or something like that. But I didn't talk about acid base, or I didn't talk about anything. So after that question, then I really rethought, here I am, a chem major, and I can't even answer such a simple question like that, And then I looked back at, how the chemical reactions were presented and how they're covered, and I realized, wow, based on this, I probably wouldn't still not been able to answer it, unless I was a specialist working in phosphate. But now it's so easy because, given it some thought, there are only 3 types of reactions I needed to talk about, right? Metathesis. So I could have said, phosphate will precipitate out with all these ions, except not these ions. And then acid base, phosphate's a powerful base, almost as strong as hydroxide. And then redox, phosphate would be an oxidizer, but, even though it's +5 for the phosphate, it's not a powerful oxidizer because it doesn't occur. Have you seen phosphate as a powerful oxidizer on the chart? Have you even seen phosphate on the chart? That means its acid-base properties and its metathesis properties must be much more significant than its redox properties, because phosphate's a very common ion, and yet it's not on our redox chart, So those are the kinds of conclusions you can come up with. But that was one of those things that, it was a kind of a grueling experience that couldn't, and the dead silence was killing. But it seemed like forever that it took me to come up with not a very good satisfactory answer, but it probably wasn't that long.
But did you pass the test?
Yeah, I passed it. But I guess that wasn't the only question. If that was the only question, I was in trouble. But there was lots of questions.
I have a quick question. On the homework, you said don't go over the corrosion. Does that mean everything past the corrosion, or does that mean just the 4 questions?
No, don't go over corrosion and on, except you have to look at the advanced problems, too.
So no electrolysis reactions, and the advanced problems start at 75.
They're being skipped from like
50,
40 something?
59 to 74 is what's out apparently.
Oh, never. You're so freaking late.
Well, good assistance there, Phil. I like that. You can be my spokesperson.
Nothing has been said.
Yeah, so when you guys write a paper, like the titration paper, Scott, just lift up your door a little bit.
Don't turn it up.
And it should be okay. That one would close. when you write the paper, you should write it from the point of view that somebody's going to disagree with everything that you do. You know, like for example, how you got the equivalence point. Somebody's going to say, no, that's not right. It's a little bit this way or a little bit that way. You know, and so you want to provide, well, you know, you want to provide enough arguments to say, no, that's ridiculous. You know, you're wrong. That's what I want. And so the same kind of thing goes with the test. You know, I know this. I did this right. You know, there's no multiple choice answer that matches here. You're wrong, you know? That kind of thing. Because, you know, on the practice test, number 8, even though number 8, you know, I did that in class, and we got the right answer, 0.032. But on the practice test, the right answer wasn't there, you know? It was 0.32, not 0.032 on the practice test. This is for chapter 19, number 8. The one you just...
What pressure does water go to a gas at 25 degrees C?
Maybe this is not a fair. Maybe this is a. Oh, the one I put. This is what I want people to do. You know, for number 8, and this happened, when I gave this test, people came up to me and said, there's no right answer here, right? It's wrong. And so that's what I want people to do. I want them to be, you know, those hypercritical people in the audience, you know, looking at the scientific data. But yeah, number 8, there's no right answer here because I made a mistake. And so I did this one in class, you know, just to, because I always do this one in class, but I did this one in class because I want to make sure that you guys had there's a conflict there. And so actually it was supposed to be 0.032, not 0.32 for number 8. What was I talking about earlier? So, well, anyway, if you write the report in that context, it'll be great. Okay. We should let's take a break now, and then we'll start again. I'm going to, we're going to do a lab today, but it's going to be a dry lab when we get to chapter 24. Yeah, no big deal. Actually, I don't have it with me.
Stretch our legs, man, for a good day.